Hello. So we're back again, and we're going to continue our conversation about cartography with map scales. So earlier in the lecture, I talked about this idea of spatial scales, the way in which we view the world at either a small scale or a large scale. A map scale is just a representation, a measurement of that fraction, of that scaling. In other words, get this thing to work here. How much have we reduced the real world? So when you're looking at a map, right, how do you know what the scale is? And you should be able to find on any decent map one of these three types of scales. A bar scale, you've probably seen this here. So this might say that this bar on a map, this distance from here to here is 20 miles. And this distance is 30 miles. And you could take a ruler and use that measurement and figure that out. That in the real world, this is 20 miles. You might see a verbal scale. 1 inch equals 28.5 miles, or 1 centimeter equals 18 kilometers. And then you would just take a ruler and you'd measure on the map. Oh, it's 5 inches? Well, 5 times 28.5. And then the last one is the fractional scale. And you just make it as a ratio. So 1 to 1.1, sorry, 1 to 1,806,000. What does that mean? That means that one unit of measurement on the map, so whether it's an inch, a millimeter, a meter, whatever it is, one of these on the map in the real world is 1,806,000 on the Earth. So that's the fraction, if you will. 1 inch would equal 1,806,000 inches in the real world. So that's another way of showing it too. These can all be converted. I mean, you could actually do this. You could figure out how many inches are in 28.5 miles and do that as well. Another thing a map should have, many elements, like a map legend. So you see a map and you see symbols. How do you know what these mean? The map legend or key might tell you. Why are some roads black and some roads gray? Why is this blue? Why is this green? Most of us know a lot of this, but maybe you don't. Other things like direction, maybe an arrow pointing north or south. So here's an example. This is a map of a school and the surroundings, right? But maybe you're thinking for lunch you want to walk down by the river, have lunch at the river. Well, do you know how far it is? If you've never been there, you're not really quite sure. I mean, you could kind of guess, but if you had a map scale, you would know that this unit right here is about a mile. So from this building here, that's about a mile, 2 miles, 3, about 3 to 3.5 miles to the river. So unless you're really, really physical fit, I'm not walking 3.5 miles for lunch. That's just me. Now you know. Another thing we can measure with a map is elevation. So we can show hills and valleys, and we use contour lines, right? These are, on a flat map, contour lines, and these represent equal areas of elevation. A map like this is called a topographical map. It shows elevation, it shows hills. So on this map, everything that is on this line marked 10 is 10 feet above this line. And then here's 10, 20 feet, 30 feet. So every point on this line 20 is 20 feet up, and you draw it on a hill. And that's how you can represent elevation. We usually indicate this as, say, 10 feet above sea level, or in our case in Chicago, 580 feet above sea level. Sea level is usually considered 0 around the world. Okay? A couple things about contour lines. They always connect back to themselves. They always make a loop. The loop may go off the sheet of paper. If you cut the paper in half here, right, they won't close off, but they would continue it. And why? Because someplace always is 20 degrees or 20 feet north. It never stops being 20 feet and then it doesn't exist. It always does. So secondly, they can never cross each other. These lines can never cross. Why? Because if you have two lines crossing, if the 30 feet above and the 10 line feet above crossed, that would mean that place is simultaneously 10 feet above sea level and 30 feet above sea level. Well, we know that can't happen. What they can do is they can get very, very close, like a cliff, and I'll show you what that means, but they can never cross each other. Here's an example. Here we have a nice volcano, very common shape, right, the nice cone, and you can see that this is 500 feet above sea level, 1,000 feet, 1,500 feet. So every point on this line, and it forms a pretty nice set of circles. And so you can see that from here to here, right? It goes from 500 to 2,000. In the middle is about 2,400 feet, right? Now, here we have another hill, but here one side is much steeper than the other. And you'll notice that the contour lines here are much closer. So one thing you learn looking at a topographical map is that the further apart the lines are, the flatter the surface is, and the closer they are, the sharper or the deeper the cliff. All of these can be combined with remote sensing. Okay, how do we actually make maps of the Earth? So the first part today is remote sensing. Remote sensing just means that we are collecting the data from a distance. And most commonly today, that means satellite imagery. So satellites in space use many different types of sensors to acquire data. Probably the most common is photographs, pictures, but you can use other things as well. We also use radar. So if you've ever watched a weather forecast and they show the rainstorms coming in, right, with the big bands of orange and red, which are thunderstorms, or green, light rain, they are using radar to actually measure precipitation in the clouds. We can use sound underwater. So light only goes so far in water, but sound can penetrate the deepest, and we can actually use sound waves to map the ocean floor up to 7 miles down. And a new thing we're using now is LiDAR, or laser light. So here's some examples. With satellite imagery, we can actually measure temperature. We can use infrared monitors on a satellite to measure ground temperature. And this shows you here, this was actually measured during a drought. It measured the temperature of the Earth. And if it's very, very hot, that was a drought. We can also use it to measure water temperature. Or, this right here is using a regular camera to measure visible light. And we're measuring here, there were fires here in Mexico. You can see the smoke going into space. Here's an example of radar. Doppler radar can actually measure distance and bearing, or speed. We send out a pulse of energy. It's actually microwave energy, the same thing in your microwave, out into a rain cloud. And when it hits a drop of rain, it bounces it back. And we can actually measure how long it took for that to bounce back, like an echo. And it tells us how far away it is and how fast it's moving. And we use computers to map that. So here we can see a hurricane, and indicated in this, you see the pattern, the swirling pattern. And the darker the red, the harder or more rain there is. By the way, Doppler radar, you notice the word microwave. That's how we actually invented microwave ovens. When they were designing the first radar sets in the 1930s and 40s, one of the scientists noticed that whenever he was doing experiments with the radar, his chocolate bar would melt in his pocket. And so they discovered that microwaves, which are the same things that we use to cook our food, are also in radar, can cook food. So your microwave oven at home is actually a small radar. It's just the microwave box is shielded so the beams don't come out. So with sonar, we can do the same thing as radar, but underwater. They can send down sound beams. So a ship is out in the ocean, it sends a sound wave down to the bottom of the ocean, and it reflects back like an echo. And you can use that echo to determine depth. The longer it takes for the echo to come back, the deeper the water is. And so here we actually mapped the underwater areas around the Hawaiian Islands. This is Hawaii. The gray parts are the islands. But you can map underwater and see that there's actually a lot of the islands are just below the surface. They're much larger. And we've been able to start to map much of the ocean's bottoms this way. LiDAR is basically the same concept, but here you use laser beams. So an airplane or a satellite will fly over an area and send down a laser beam, and the light will reflect back. And this is extremely accurate. So this is what they call a digital elevation model of the Earth, elevation being height above or below sea level. So you can see the mountains right here, flat plains, very, very accurate. All of this sensing, the LiDAR, the sonar, all of this stuff, today when we make maps and we analyze the data, we plug this all into a GIS, a Geographic Information System. And this is basically a computerized mapping software program that takes all this data, it analyzes it, it allows us to make maps and compare and display it. So let's kind of go what this means. What they're basically maps, what are the advantages? Well, because they're computerized, they're interactive. You can choose which information to display, what not to display. You can animate it. You can gather new data. So as you gather better data, maybe you don't have radar of this particular area, and now you do, you can upgrade it. You can also choose the different types of data to go into it. Maybe you just want to monitor ocean temperatures at the surface. Then you can exclude land temperatures. Maybe you want to add in wind speeds. Maybe you want to measure many different things. So you can take all these different layers of data and manipulate them to best serve what you need. So that sounds all very well and maybe probably confusing. But I would say that most of you have actually used GIS without even realizing it. So this right here is from Yelp. Now, I don't know if you guys have used Yelp. It's an online service. You can plug in, I want to go show me coffee and tea shops that are near 30 East Lake Street or Harold Washington campus. So here it is. There's 30 East Lake on a map. It shows all these coffee shops, right? They all have numbers. You can click on a number right here, and it tells you a little bit their name, what they serve, their address, some reviews, right? And you can modify. Do you want to show by neighborhood? Do you want to show by a bird's eye view? Do you want to zoom out? Do you want to narrow by price? Maybe you want a place that is open now, or maybe they serve. You can narrow, you can add and manipulate all these different filters. That's a GIS system. Maybe a more common one. You want to get home from Harold Washington. So you go to Google Maps and you type in a location of where you're at, location of where you want to go, and it gives you some options. You could walk, you could bus, different ways. You could bike, and it finds all these different layers. Here's a layer of CTA red line. Here's a layer of bus routes. You see a layer here of surface streets, of features like water, parks, and lakes, specific locations, and it combines all these layers and you can manipulate it. And that's a GIS system. This one is from the state of California, and they used GIS data. They had data about streams and lakes, what type of areas grow what type of plants, the rainfall records, what areas had hills or valleys. All these different types of data were integrated into a map, and it built a map that showed fire threat. So what areas have the highest risk of forest fire, right? And you can see the darker the red, the more the risk. And so it analyzed all these different layers, and they were manipulated to create the map they wanted. And this is what is used quite often by state governments, by scientists, as a GIS system as well. All right, I'm going to pause for our last section. So again, if you haven't gotten something to drink, that's on you, but we'll see you back with the last part.